Alright, so we finally made it to Unit 5 in Anatomy and Physiology. So keep in mind that what's in the lab manual from pages 130 to the end, that's kind of, again, your Bible, what you got to know. So what I wanted to do was, again, I spelled out all the notes for you, and I know you can read them as well as I can. I just want to make sure that you do know the finer points and that you emphasize many things whenever you're actually going over these things and studying them. Now, understand that the final practical doesn't have a pick list. Why? Because it's kind of like a quiz where you'd have matching. Kind of there's the list and you pick from the list. But it's going to be on the respiratory system, the male reproductive system, the female reproductive system, as well as the menstrual cycle. It's a model of the menstrual cycle for the female, obviously, and then there's going to be 3 Punnett squares on it because, again, the last unit goes over human reproduction, development, that type of thing, and embryogenesis, which you guys know, talking to me and what I do, it's kind of my bag. Alright, so I will take you by the hand when I go through later ones of these, and I'll walk you through Punnett square problems. You don't got to freak out. I'm going to show you a very simplistic way to attack it and break it down, and basically if you set it up the same way, you follow the pattern, your chance of getting it wrong is little to none. You just have to be able to attack it and have a logical way to go through it. Alright, so, but that won't be till after we cover all this respiration stuff. So, respiration, if you saw the outline online, again, when I set it up, I go over, it's kind of like what I always do. What is the importance of the respiratory system? Then I go over the gross anatomy of the respiratory system. The parts I'm going to go over, obviously, they're not negotiable. You got to know what they are. If you look in your manual, what you see are very detailed diagrams of the larynx, which is your voice box. There's a reason why there's so many pictures of it, if you get my drift. Additionally, then it's just the gross parts. Same thing for the male and female plumbing. I mean, how well you know their plumbing, I don't want to know, but you should be familiar. God, I hope so, with your own plumbing, and then the opposite sex, you should kind of know what their plumbing is, how it works too. But again, I'll go over that at another one of these things. All right. So if you grab the outline off canvas, so again, purpose of the respiratory system, you understand. There's many of them, but the major one, as you understand, is going to be gas exchange. The whole major thing is going to be able to get oxygen into the cells that need it, into the tissues that need it, so they can do aerobic cell respiration, the whole 38 ATP per glucose, and then also remove the waste. Because most commonly, again, if you go through the aerobic respiration equation, carbon dioxide. Now, a couple things you got to really understand and emphasize as we go through this. Your blood doesn't want oxygen. People have this misnomer that, oh, I know what respiration is. That's no, that's a dirty phone call is what that is. That's just you huffing and puffing in and out. That's nothing. There's going to be 2 phases of respiration which you have to know. There's what's called external respiration and internal respiration. External respiration means getting the gas into your lungs to the level of your alveoli, your air sacs. Internal respiration would then be, how does the hemoglobin pick it up? How does it travel in the body to where it's going to dump it off, and come back around and get more? So, real simple. Anything from the air sac up, that's external respiration. Anything from the air sac down, basically in your body, that would be considered internal respiration, okay? So, when I go through the gross anatomy with you, that's all going to be parts of the external respiration, because that's just getting it in and how's it processed, get in. When I go over the physiology of how to load the blood with oxygen and unload carbon dioxide, that's the internal part of it. But that will be probably the next lecture in this series. This part, I hope to get over the nuts and bolts of the respiratory system, more or less, so you can distinguish what the parts are and how they are. Also understand, too, I played devil's advocate. At the end of your outline, I made sure I included diagrams of the respiratory system, what's called the pharynx, which is essentially your throat, the sinus cavity. There's the 3 pictures of the larynx. There's the lungs, and then last but not least, the alveoli. So when I refer to my pictures, I'm referring to the ones that you have in the back of your outline already. Plus, there's also ones, obviously, in the lab manual as well, too. All right, so functions of the respiratory system. Again, hands down, the most important obviously is gas exchange. Oxygen in, CO2 out. Now, like I said, your blood does not want oxygen. Think of your blood kind of like you take a soda can and you crack it open, okay? If you let it sit long enough, what happens? It goes flat, right? That's your blood. Your blood does not want oxygen. The oxygen in the blood is essentially small bubbles. In given time, the gases of the oxygen have more kinetic energy than the liquid, and they want to get out. That's why soda pop goes flat. Same thing with your blood. So then how the hell does your blood move oxygen? Big, huge star, hemoglobin. Without hemoglobin, none of this is going to happen, okay? Hemoglobin has a small amount of iron in it, heme, with globular compounds around them. 4 of them, actually. There's 4 iron particles per. So what that means is that each heme can hold roughly they can hold 4 molecules of oxygen. Now, you remember back in histology when we looked at the blood smear. I know you saw those little tiny pink balls that were erythrocytes, red blood cells. Well, understand that each erythrocyte is going to have roughly about 250,000 hemoglobin molecules in it. Let's do some simple math. That means 1 red blood cell, each hemoglobin can carry 4 oxygens, and there's 250,000 of them in 1 red blood cell. That means 1 red blood cell can hold saturated 1 million molecules of oxygen. That's our transporter. Hands down, the most important part to get oxygen and where it needs to go. Now, hemoglobin, however, also has 2 jobs. It's going to pick up oxygen, but it also picks up carbon dioxide. Now, if you remember our talks about enzymes, enzymes have active sites where things will bind and be moved around, and can also chemical reactions. Hemoglobin is unique. It has the binding site for oxygen is at a different part of where the binding site of carbon dioxide is. Therefore, carbon dioxide does not interfere with the binding of oxygen, nor vice versa. So basically, you have a molecule that acts like a transporter for 2 separate molecules, where one does not interfere with the other. Evolutionarily, brilliant. Understand, that's brilliant. All right, now, so the first thing obviously is going to be gas exchange. That's the most important one. Number 2 is what I'm doing right now, speech and vocalization, but that's, not that important. What you got to understand is, if you were to look down in my throat, into my larynx, what you would see is a tube with an epiglottis that flaps on top of it, okay? Well, if I went, that epiglottis would flop open, therefore letting air out of my lungs. Now, there's going to be 2 sets of vocal cords, which I'll go over in just a little bit, but the ones that are the most important are not the superior, they're the inferior folds. And therefore, whenever you push air through these folds, think of it kind of like when you're a little kid and you put a blade of grass between your thumbs and you made a whistle and it vibrated. Same thing, same process. But you got to understand is that tissue that does that, it's connective tissue, which means if you strain it, if you scream, if you do harm to it, you can damage it, it can scar, it can get lesions on it, it can have all sorts of problems with it. So therefore, basically you want to treat your voice nicely. You don't want to scream all the time. Think. You ever see a little girl, 3, 4, 5 years of age? She's the screamy, meanie little girl, always screaming. You talk to her when she's 13, she sounds like a grandma that's been smoking a pack of Luckies for 40 years going, "Hello, darling, how are you?" The kid's 13 years old. That's why, because she scarred up the tissue. All right, now, next thing that's also part of the, considered part of the respiratory system is the olfactory system, meaning sense of smell. You know all these parts already. If you remember from the skull, you have the vomer, and you have then coming down the perpendicular plate. The perpendicular plate in your nose is from the ethmoid bone. The vomer is its own bone. What does that do? It's going to separate your nose in the left and right chambers. But then you remember back when we went over the skull, the conchi. You had the inferior nasal conchi, the middle nasal conchi, all those little bumps that went on the inside. And what did I tell you those were for? When you go, the air slows down and it swirls around in your nose. Well, why? Because there's mucous membranes in your nose. What is that for? It traps dirt, dust, pollen, particles, all sorts of stuff. But more importantly, all the way up here, if I were to take your nasal bone and rip it out, right back there, think of like where your tear ducts are. If I went in about 1/4 inch, there's that flat plate. Think in the skull. If you remember, there was, when you took the skull cap off, there was the cribriform plate with the crista galli sticking up in the middle, and there's all those little holes everywhere called the olfactory foramina. The olfactory foramina are live nerve endings, and they go right into your olfactory bulb in your brain. Well, the other side, on the bottom side, is covered with a mucus layer, and therefore you have basically protein receptors. So when you go, whatever proteins get attached to which receptors will trigger a nerve and then go to your brain and tell you, oh, that's a cupcake. Oh, that's dog poop. That's how you trigger it. Now understand, as far as things that trigger memory, olfaction hands down is one of the most powerful things that trigger memory. Just think. You haven't been to Grandma's house in forever. Grandma unfortunately passes away. Somebody who's packing up the house decides, oh, well, you might like this from Grandma's house. You open up the box. Before you even take the paper off of it, all of a sudden you get a whiff. Where are you? You're back to being 5 years old, sitting at Grandma's table, just like that. It's a very powerful, powerful trigger of memory. Okay? Now, number 4 on your list, huge star. One of the biggest, most important things that the respiratory system does, aside from moving gases, is going to be to adjust your blood pH. This equation is important. So, keep in mind, whenever it rains, so the same process happens, but in a slower way. When I take carbon dioxide, I'm not going to balance the equation, keep in mind, and you combine it with water, okay? That is going to form a very, very weak acid called H2CO3. That's called carbonic acid, okay? It's the same stuff that falls on your head when it rains. So rain is actually acidic naturally. It's only considered acid rain once you go below a pH of 5.5. Now, this, however, will break apart into 2 separate things. H plus hydronium and HCO3 minus bicarbonate. This is called the bicarbonate buffer system. This is how your blood pH stays where it needs to. It's one of the most powerful buffers you have in your blood, in your whole blood serum. Why? Because as long as you're alive, you're always making carbon dioxide. Your cells are always giving it off as they respire, so it's plentiful. Unlike oxygen, your blood loves carbon dioxide, sops it up like a biscuit, and wants to hold on to it, okay? Because it's part of this system, all right? Now, this one is important. It's the bicarbonate buffer system. Next thing on the list you see there is that lungs carry out the last step in what is called angiotensin II synthesis. What's angiotensin II? It's a hormone that regulates your blood pressure. So therefore, it helps to monitor your arterial pressure itself. Breathing gradients, again, by you going in with your chest, what you're doing is you're causing pressure gradients within your thorax and with your abdomen. Well, what does that do? You understand when your heart pumps, there's an arterial pressure that actually pushes. Well, then you got to bring the blood back. That's called a venous pressure. By you breathing, you're creating pressure gradients which act like bellows, which help to pull the blood back to your heart. Additionally, in your neck, under your arms, in your groin, you have lymph nodes. Well, what is that? Basically, if you take immunology with me, we'll go through the whole gambit of it, but more or less it's part of the immune system where bits and pieces of protein things will fall through. And the lymph node basically looks like a mesh. Whenever it finds something foreign, meaning with the protein receptor finds something foreign, it will swell. And when it swells, what's it do? The mesh tightens, which means whatever it found can't go further until the immune system identifies, clears it out. That's why when you get a sore throat, you know, your glands swell. Same type of idea. Now, why do I mention all this? Because by you breathing in and out, you're actually improving the movement and pressure of lymph around this area for your lymph nodes. Last but not least, you see there, number 7 is my favorite, which you know it can't be right. This is often called the Valsalva maneuver. What's it mean? It means, okay, you're going to make a number 2, okay? You're on the can. Before you push, what do you always do? They always go, hold their breath and go, That's actually called the Valsalva maneuver. Don't laugh. I'm trying to teach these people. All right, that's called the Valsalva maneuver. So basically, the Valsalva maneuver is whenever you take air into you and you hold it down and push down to increase the pressure of your insides to make it easier to expel contents to the outside world. So when you defecate, when you urinate, when you vomit, all of that is, you think about it, you always go, huh, and then you do it. So anytime you feel yourself, always take air in and go, huh, Valsalva maneuver, okay? It occurs during childbirth, it occurs during sex, it occurs all the time. I feel bad for the guy named Valsalva, because forevermore, his name's tagged with it, but I guess you couldn't be, it'd be worse if you were Joey Sphincter. That's another one. Yeah, see? Yeah, all right. So, now, we go down to the gross anatomy. Now, the gross anatomy is the upper and lower respiratory tract. Real simple. From your voice box, from your larynx up is the upper respiratory tract. From your trachea down is the lower respiratory tract. Okay, and it ends at the alveoli. So let's run through this. First thing, obviously, you understand is your nose. Now, what we're looking at then, if you want to look at this, that's going to be this diagram right here, the sinus passages, okay? So, the nasal passage, your nose, basically, what's it for? Major thing is when you take air in, when you go, what's it going to do? It's going to cleanse the air, and it's also going to humidify the air before it gets into your lungs because you don't want it to dry out. Additionally, by it going through there, plus also through your mouth, it helps you warms the air too. This is going to be important later when we talk about why the lungs inflate, because you know when you take a gas and you heat it, it expands. Well, when it expands and you go, your body is warmer than the outside. The gas can expand and helps to inflate your lungs. That's going to be an important law. That's going to be Charles's law when we get to it. All right, now, gas laws. All right, so the nose itself, understand, is going to have different portions, okay? So your nostrils, okay? Your nostrils are called one of two names. They're either called nares or choani. Both you have to know. Now, how many pairs of nostrils do you have? 2. You have an external and an internal. Now, you can say you've never done this, and if you do, you're a damn liar. You're sick, you got a head cold. You ever hear somebody always go, and then they, well, when they do that, what they're doing is taking the mucus that builds up in the sinus passages, and they're shoving it down through the internal choani. Those internal choani then are what then will then lead to your esophagus, and then basically you would eliminate it with your stomach acid. You're like, that's disgusting. I would never do that. Follow something here, guys. If you're well, your nose produces about a quart of mucus a day. Where the hell does it all go? Right, down your esophagus, into your stomach to be cleared. Because what's the mucus for? It's immunological flypaper. It catches everything that's coming in, the impurities, the dust, the pollen, fungal spores, whatever, and there's lysozymes in it to destroy it, so therefore you stay healthy, you stay okay. All right? Now, but that's your external and internal choani. You have to know both. All right, what else? So I told you what the nose does. It warms and humidifies the air. Also, obviously, it detects odor with the olfactory epithelium, as I mentioned. The sinuses are just basically as a novel thing. They're a resonating chamber. You'd know this as a kid or as an adult. When you're talking and you hold your nose, your voice changes. That's because it's a resonating chamber for your voice. It's a function, but not a really important one, I understand. Now, let's see. I already went over the choani. I went over the internal. Okay, now we're going to go to the internal portion. Okay, so imagine you're going to pick your nose. Again, if you say you don't pick your nose, you're a damn liar. It's just a matter whether you're caught or not, because everybody has something stuck there and you try to nonchalantly get it out or whatever. It's kind of like if you had a wedgie, you nonchalantly, everybody has them. It's called the fact of life. So you got to take care of these things. All right, so let's say you're going to go pick your nose. You stick your finger into your nose, okay? Now understand your nasal bone is right here. Your nasal bone is kind of important because people, they're not the brightest. If you were to take your finger and shove it in, you're only going to get in about that far because your nasal bone stops you because your fingers are like sausages. They can't get all the way in. That's good. Why? Because where your ethmoid bone is right there, and you know how thin it is. We saw the cribriform plate. If you didn't have the nasal bone, it kind of acts like a speed stop, so you don't go too far in. You don't shove your finger into your brain and kill yourself. Which, walking around, you hope some people didn't have that stop and they would be dumb enough to pick their nose to death. But, it doesn't happen. You actually have a backstop right here. All right, so this area right here that you would actually pick, that is often called the vestibule. All right, so let's continue on, coming on down. So the vestibule, as I said, your nostrils spirit into left and right nostrils. Again, by the vomer down at the inferior position and the perpendicular plate in the superior, making it left and right. All right. Now, in the vestibule, then, you understand you're supposed to have, nose hairs. People are like, you have to have nose hairs. Why? Think about water coming into a water treatment facility from everywhere, okay? That water can be exposed to not just in a pipe. I mean, it could be exposed like as a canal or whatever, and there could be stuff floating in it, branches, tire. You don't want that getting in the water treatment facility. So the intake pipes of a water treatment facility have these large metal grids on them so that anything large particulate gets stuck. So therefore, as the water comes in, we can more easily purify it. That's what your nose hairs are. Your nose hairs are this mesh to prevent larger particles from actually getting into your upper and lower respiratory tract. Your nose hairs, proper name, are called vibrissae. They're also called guard hairs as well, too. All right, going back then, as we know then, I said that, please note, star bedazzle, the type of tissue that lines this area, is our old friend pseudostratified ciliated columnar epithelium, okay, with goblet cells. The goblet cells, ding ding, make mucus. Now, this type of tissue is found, starts in your nasal passage, will go all the way down your trachea, will go all the way down into your bronchial tree. Once we get to the air sacs, it stops. What's found in the air sacs is going to be squamous epithelium. That's significant because that means squamous epithelium do not have cilia, which means if something gets in the air sac, there's no mean to get it out. There's no way to propel it out or to get it out. But think about it, from your nose going all the way down into your bronchial trees, you have this massive series of tubes and flypaper to prevent anything from getting into that air sac. So by then, it should be pretty much picked clean by that point, you would hope. No pun intended. All right, so let's see. Again, in there, just something you might find on Jeopardy one day. Inside your nose, you have what's called an extensive venous plexus on the inside. It's an extensive series of small blood vessels. Give you an example. You're coming down with a cold. Do you ever notice that whenever you come down with a cold, you're going, and then one nostril is clogged and the other one's open? You're like, what the hell? And then you wait about an hour and you go, and now the other nostril's open and the other one's closed. What the hell? Right. This is part of this blood. The blood flow to this area. The whole idea is to alternate between left and right nostril, basically letting blood constrict and then flow out, constrict and flow out. It alternates about every 45 minutes to an hour. Why? Well, that's so that whenever you're breathing through your nose, one is getting air into it while the other one is constricted so it doesn't dry out. Therefore, as the other one, as you're breathing through it, is drying out, eventually it closes to re-moisturize, the other one opens, and you can continue to breathe through your nose. Okay, now, moving on down, we now come to your pharynx. Please note the spelling. It's not pharynx, it's pharynx. Pharynx means your throat, okay? There's three reasons to your throat. You have your nasopharynx, your oropharynx, and your laryngopharynx. Nasopharynx means... where the hell did I put it? There it is. All right, so nasopharynx. Now follow. Nasopharynx. Now your sinus passages, notice, come in, and then you make this right angle straight down. Okay. So let me just draw it out. So this is going to be a really bad drawing. All right. So there's your nose. Okay. There's your mouth right here. And I'll give you lips. Okay. Well, that's bad. But anyway, there's your mouth. All right. And there's your tongue. All right. Okay. Those are going to be. Okay. Good enough. All right, so understand that means when you breathe in, the air is going to come in, it's going to swirl around, and it's eventually going to hit the back of your throat. Okay, that's whenever, right here, when you hit the back of your throat, that's when somebody goes, and they swallow it. That's the internal choani. At that point, that's the sinus passage. From that internal choani down, then, oops, that's where you start the pharynx, the throat. Okay, so again, if this is your mouth. Again, this would be your oral cavity right here, okay? This is going to actually form a tube which comes down to link this and eventually come all the way down. Your voice box would be right here, okay? All right? So that means from when you breathe air down and you make this 90-degree angle down, that is called your nasopharynx. At the back of the nasopharynx, you have a set of tonsils. Why? Well, think. When you go... Air is a gas. It has the ability to make that quick 90-degree turn going all the way down. But if anything is solid in the air, spores, dust, whatever, they have momentum. Can they make that quick 90-degree turn? No, because they have momentum. As they get pulled in, they smack into the tonsil. That tonsil then destroys it for you. to help to prevent it going into your lungs. Okay, that is not the tonsil you remove whenever you have tonsillitis. Those will be your lingual tonsils and also the tonsils on top of your mouth. All right, so back here, if you see, you want to go over nasopharynx. That's going to be your pharyngeal tonsil, which again is never removed. Now, once this air comes down, we're now basically in the back of your throat. So if you were to go ah, you're looking at the back of your throat. Think where your uvula comes down. You can see that. That is now called the oropharynx. So the oropharynx starts at the bottom of the back of where your tongue is, the tongue root where it's attached to you, and also back to where you have your uvula sticking down. From there back going down, that is called the oropharynx. Okay. Now, understand that means air can come into this area two different ways. It can come in through the nose, it can come in through the mouth. Doesn't make a difference how it comes in. Eventually it merges and eventually it's going to go down to your lungs. All right. Now, the oropharynx, that's where you have your tonsils that you would get removed if you had tonsillitis. You have your palatine tonsils, which would be the ones on the upper side, and then you'd have your lingual tonsils, which would be the ones down when they go and you see them down below. Those are the ones that are removed during a tonsillectomy. All right, then all the way down here, you would have your voice box. The tiny little area right above the voice box, the larynx, that's called the laryngopharynx. That's it. Okay, it's a little tiny area right before we transition into the voice box, larynx. All right, so what is the purpose of the pharynx, your throat? Think of your respiratory system as a series of pipes that you PVC to get to lock together. Well, you have to get it from point A to point B. The pharynx is just accumulating the air and channeling it into one area to attach to your voice box, your larynx, the next stage. Okay? Now that covers the pharynx. Now we come down to the larynx. Now again, remember, the larynx, there's lots of diagrams in your manual. You need to know these parts that I'm going to go over with you. Well, first off, let me get rid of all this. Now, the larynx, more commonly known as the voice box, what's its job? Think like you're using a vacuum cleaner and you're trying to put an attachment on it. That attachment has to go to a hose. Well, to do that, you need an adapter at the end of the hose attachment to fit to make sure you get a good seal before you go to the hose. That's what the larynx's job is. Your larynx sits right on top of your trachea. Just take your finger and run your finger up and down your trachea. It feels like vacuum hose. Right, that's hyaline cartilage, C-shaped rings which are holding it open. That's when they do a tracheotomy to open you up. But the C-shaped cartilage rings that snap in. All right? There's nothing holding it open. There's no bone, there's no structure there. It's just cartilage holding it open. But it's a vacuum hose and the larynx has to sit down on it in order to make a good seal. All right, so when I draw this, I'm drawing it like I'm facing you, okay? So what you have to understand is coming up forward, you have that bone, which you know is a very unique bone in your neck, called the hyoid bone. Unique because it's the only bone that doesn't articulate with any other bone in the body. It sits right there, okay? What does that do? Holds the airway open. Below that, then, you would have, let's see if I can draw this correctly. You have this large piece of cartilage in front. If you're a male, that would be what you would call your Adam's apple. What is that called? This is called thyroid cartilage, big star. It's one piece of cartilage, it looks like a big shield in the front of your throat. Well, think now, in order for then as the air comes down, this thyroid cartilage has to have a connector to the trachea down below that. If you look below this, there's a little piece of cartilage below it. That area, that's going to be called the cricoid cartilage. It's the actual connector to it. And then you then have your vacuum hose going all the way down your trachea, okay? Now if I take this and spin it around to the back side, okay? This cricoid cartilage actually comes up and makes this huge platform. So if I spin it around, this would now be the back of your hyoid bone here. Has the little horns, okay? Now, what we're looking at then is the thyroid cartilage would be behind my whiteboard, okay? What you would see then is this large piece of cartilage come up like a pedestal, and then you'd see the trachea, like you saw on the bottom. Now this cricoid cartilage is big in the back, and then I understand it wraps around and underneath the thyroid cartilage. Okay, so the cricoid cartilage, that's this one. That one is going to be the connector to it that sits on it. Well, I'm speaking. How is that possible? Well, coming off of this cricoid cartilage, there's going to be these two little columns that come off of it. Okay? Now, so if you're following the notes, we're down to where I have the larynx has 9 cartilages, okay? 9 cartilages I went over. The thyroid cartilage, epiglottic is unimportant. Thyroid cartilage I went over. Cricoid cartilage I talked about. Now, these two little pedestals that come up, those are called arytenoid cartilage. Now, the arytenoid cartilages, notice there's 2 of them. They occur in a pair. That's important. Also, these arytenoid cartilages will come out and they'll make a point. Those little points are going to be called corniculate cartilages, which means little horns. Again, they're in a pair. Well, who the hell cares? That's where your vocal cords are attached to. So as the arytenoid cartilage and the corniculate cartilage, as muscles move on them, if they pull tight or let loose, your voice either goes high if you make it pull it tight, or it goes low if you let it lax. So that's what's controlling the actual pitch of your voice, is this cartilage with the muscles. Okay? So, understand then, I said there are, 7 cartilages? There are 9 cartilages. Thyroid cartilage is 1. Cricoid cartilage is the second one. Then we have the other occur in pairs. We have 2 arytenoid, 2 corniculate, and the last one you see that occurs in pairs is going to be then the cuneiform. Again, unimportant, just note it occurs in a pair. The major ones I pointed out to you. Now, keep in mind, as I showed you with the model numerous times in class, where, if I were to then take your throat and then look down on it, okay? So this was the back side of it. I'm now going to take your throat and look straight down into it. What you would see is a hole. That hole is called your glottis, okay? Well, the glottis is the opening which is going to go to your lungs, okay? We've done this before. Well, understand, over this is now a piece of cartilage that will now flap over the glottis whenever you swallow. Why? You've done this with me before. Take your fingers, grab the back of your throat, and then swallow. What do you feel? You feel your whole voice box go up, and then you feel your tongue pushing down the back. What is that doing? It's taking the epiglottis and just closing up the windpipe. Why? As remember in class I told you, when people choke on something whenever they're eating and talking or drinking, they say, oh, it goes down the wrong pipe. Exactly, it went down the wrong pipe. The front pipe is your trachea. The one right behind it is the esophagus. So if you're talking while you're drinking or eating, the epiglottis flops open, and then when you drink, the food and water don't know where to go. They get confused and go down the wrong pipe. They go then into the trachea instead of going down the esophagus. Now, the good thing about this is that when you swallow, you have a fail-safe. When you swallow, the epiglottis should close. Okay, it should flop over, kind of like a trash can lid. Okay. However, also when you do that, the glottis itself will pinch close itself. Okay. So the glottis, the opening going into your lungs, has 2 layers. There's a superficial layer and there's a superior and inferior layer of what are called vocal cords. The superior layer are called your false vocal cords because they don't help you to speak. What they do is when you swallow, when the epiglottis goes down, the superior folds, called the vestibular folds, will actually pinch together. So basically creating kind of like a trapdoor effect, preventing anything liquid or solid from going into it. Now, the folds that are below that, those are called your true vocal cords. Okay, those are the ones that are going to be attached, as I mentioned, to the arytenoid, the corniculate, and then change the pitch of your voice as they pull or become lax. All right, hope that makes sense. All right, so now we come down. Now understand, everything I talked about right now is considered upper respiratory tract, voice box and up. Okay. Now again, note the spelling of larynx. It's not larynx, larynx. Kind of slur it together. That's how it's pronounced. All right, now we go to your lower respiratory tract. So if I were to look at you, your thyroid cartilage kind of looks like a shield, like I mentioned. Okay, that's this right here. Then you go down, and then you have these little rings of cartilage going all the way down. Well, that's your trachea. Okay. Now the trachea, what is it? It's what you call your quote windpipe. It's just connecting the piping from your voice box to go into your lungs. Now, as we get down to your lungs, the trachea is going to extend from right about here to right about, think about like a third of the way down your sternum, and it's going to branch into two, left and right, okay? That's what's now called the respiratory or bronchial tree we're going to get into. Now, the bronchial tree, think of it as a series of pipes. We start with one big-ass pipe called the trachea. It's going to split into two smaller pipes, smaller diameter. Then they branch off to make smaller pipes. Then they branch off to make smaller pipes. And then lastly, they branch off to make even tinier pipes. And then you got a big air sac on the end of it. Okay? Now, people think air sacs, they think for some reason it's like a straw. There's a big balloon on the end of it that goes, well, no. No, look. Air sacs look like a cluster of grapes at the end of what's called the terminal bronchioles. Okay? And basically, they're small. It looks like a cluster of grapes. It's not just one balloon. There's a cluster of them with capillaries wrapped all around them. At that point, in order to get proper gas exchange, the distance between outside and inside of the alveoli you're talking about is a 1-cell difference. That's for quick gas exchange in and out while the blood is going around the air sac. All right, so back to the lower respiratory tract. So you have the trachea. Please note, starbedazzle, it's made of hyaline cartilage, C-shaped rings that lock in forward. Again, they're C-shaped, which means they're flat in the back. Why are they flat in the back? That's where your esophagus is going down to your stomach, so it has to be flat. All right, now, as we come further and further down, let me go to about here. As I said, we're going to have a point where we're going to fork into left and right, okay? Like that, all right? These two tubes are called primary bronchi, the first ones. These are the ones that are going to insert into your lungs. Now, in order to make sure that that it's going to be inserted, in the middle of this, there's a small little piece of cartilage that sticks up. That is called the hilum. What does that do? Kind of like your nasal septum. Separates the air in the left and right. Okay? Now, you have your lungs. So let me see. Facing you. Your right one would be over here. It's going to be a little taller. Sorry, it's going to be a little fatter and shorter. Why is the right lung going to be fatter and shorter? Because you got your liver sitting underneath it and squishes it, making it like almost like a gumdrop looking thing. Your left one is a little skinnier and longer. I'm going to over exaggerate it, obviously. Why? Because over here then you have your stomach underneath it, so it actually can extend deeper. How can we tell left and right? People are like, oh, it's dumb. One's on the left, one's on the right. No. You have to know how to tell left and right. The most important way is the left lung is going to have an indent on the medial surface. That is called the cardiac impression. Why? Because when your heart is in your chest, if you make a fist, that's about the size of your heart. Put it where your sternum is and tilt it slightly to the left. That's how your heart is sitting in your chest. And if it tilts to the left, you have to have an indent to where the heart can go into the lung to accommodate that tilt. That's how you can tell. That's the major way to tell left. Now, so we have the trachea coming down. Make sure I didn't skip anything on trachea. I did skip one thing. All right, now, understand, this whole area is going to be lined with the pseudostratified ciliated columnar epithelium with the goblet cells. Same thing. Now, not to pick on smokers, but I'm going to pick on smokers. All right, so you understand when you smoke, the addictive agent is nicotine, right? Nicotine is a stimulant. So what does it do? A bad thing for this whole area. Whenever you do this, whenever you go and clear your throat, that is called the mucociliary escalator. So whenever you go, what are you doing? You're making the mucus from your lungs and your bronchi make these little hair balls that come up with the air pressure, and therefore when you go, the epiglottis flops open, that nasty mucus hairball comes out, and then where does it go? Down your esophagus to your stomach, and you cleared out that garbage. Okay? Now, problem with nicotine. Nicotine will take the cilia that are lining this area and it hyperstimulates them, which means that eventually the cilia are supposed to be beating slow like this to get the mucus out. If you hyperstimulate, they're beating so fast, they freeze. Well, if they freeze, they can't beat the mucus out, which means everything slides back down into your lungs, and that goes along then with other things like COPDs, like leading to emphysema, things along those. All right, so, but that's what the nicotine does. Alrighty, so now we are actually into then the primary bronchi. Now, where the primary bronchi come in the lungs, there's literally a little slit in the lung. Almost looks as if somebody had a sponge, made a slit into it, and shoved a pipe into it. That's called the hilum. That actually comes into each one. All right, coming on down then. From the primary bronchi, we go to secondary bronchi. Another way to tell left and right lung, or how many secondary bronchi are there. The right lung is going to have 3. 1, 2, 3. Superior, inferior, and medial, or intermediate. The left lung only has 2. 1 superior, 1 inferior. So again, the right lung is going to have 3 secondary bronchi. The left lung is going to have 2. All right, meaning pulmonary lobes. From there, then, from secondary, you go to tertiary. What does that mean? We go to even smaller pipes to actually inflate the smaller areas. Okay. From tertiary, well, as you know, in the tertiary, I said there's 8 in the left lung, 10 in the right lung. That's not as an important number. From there, then, the tertiary bronchi go to what are called bronchioles. Bronchioles are now smaller tubes. They're lined with smooth muscle, which is why when somebody has like an allergic attack or they have bronchitis and they're going and they can't breathe, what do they take? They use an inhaler and they squirt it in. In there, there's all sorts of chemicals. The most common one is epinephrine. What is epinephrine? It's a muscle relaxer. So that as the pipe is getting smaller and smaller and you can't breathe, the epinephrine makes the muscles relax. They open up and you can breathe again. That's how the inhaler is supposed to work. Now, the bronchioles, usually what happens is the bronchioles, the diameter is 1 millimeter in diameter or smaller. Okay? From there, then, the bronchioles, we go to what are called terminal bronchioles. Terminal bronchioles are now which are going to lead to the air sacs. The terminal bronchioles are 0.5 millimeter in diameter or smaller. Again, it's lined with smooth muscle, meaning that they could easily constrict and pinch off your airway if you have a reaction. All right. Almost poked my eye out. All right. So, good enough. So, from there, then, now keep in mind, everything I talked about, from that terminal bronchiole all the way up through the trachea, every pseudostratified ciliated columnar epithelium, everything along there is making mucus, little hairs to beat the gunk out. Once we get past the terminal bronchiole and we're in the air sac, that's it. If it gets in there, it ain't coming out, okay? Because there's no way to get it out. Now, as I mentioned, as you see in the notes, you got to know what the lungs are for. They're gumdrop conical shaped things. They're your area for gas exchange. You got that. And that's a no-brainer. Sometimes when you see questions on a test, people look at it and they, that can't be the. If it's the answer, answer it. Don't talk yourself into something that's more difficult because you think it should be trickier or it should be. Just answer the question. Just because sometimes it's just blatantly, what's this for? All right, now, the lungs. Again, you got to be able to tell left and right lung. Okay, as I said, the right lung is going to be fatter and shorter because the liver's underneath it. It is going to have 3 pulmonary lobes. Again, superior, middle, and inferior. Left lung, the side being on the left side of the body, is a little longer, more conical shape because the stomach's underneath it. Only has 2 pulmonary lobes, but the most important thing in the left lung, on the medial surface, we have a cardiac impression for the heart to go into it. All right. I go over in there about the visceral and the parietal pleura. That goes back to like the first week of class. If you remember, the visceral pleura is going to be that serral membrane on the outside of the surface of the lung. The parietal pleura is the one lining the rib cage. Each of them is going to give off a serral fluid. It's a lubricant, so when you go, your lungs aren't being rubbed against the inside of your rib cage, causing damage. Failure to do so causes something called pleurisy, which means basically think about taking your lungs and every time you breathe in, you're running them along a cheese grater. It's a new level of pain you never thought you could experience, and you can't stop because you got to keep breathing. All right. What could cause that? An infection, anything like that. But usually, it is able to reconstitute itself after the infection has passed. All right. Moving on then. We now go to the alveoli, the air sacs. Air sacs, again, big star. Again, there's not one ball. It's a cluster of them, okay, if you remember. So if we're looking at the diagrams, keep in mind what I've run you through so far. Keep losing that one. Well, I've already gone over the sinus and the pharynx. We've gone over the larynx. We've gone over left versus right. We've gone over how the bronchial tree comes in. And now, last but not least, we're looking at air sacs, okay? Now, the air sacs, really important. Again, that's where you're going to have the gas exchange. And remember, air sacs and up is external respiration. Beyond the air sac, then, that's called internal respiration. Now, the air sacs, huge star. They are only lined with squamous epithelium. Okay, so therefore they can't make mucus, they don't have cilia, they can't beat anything out. Now, your air sac, think of it kind of like each one of the air sacs, individual little ball and the cluster of grapes, think of it like a beach ball, okay? You have an outside surface of the beach ball, you have an inside surface of the beach ball, okay? Now, the outside surface, that's one of the important ones because that's where you're going to have the blood vessels around it, and that's where you're going to get gas exchange, okay? So you have a superficial layer, and then you also have a deeper layer. The superficial layer, think of it almost like not like your skin, because it's not keratinized, but it's designed to, over time, wear out and be replenished. So, like, remember how your skin was? You had a stratum basale that actually had stem cells to divide to create the outer layer. Same thing here, okay? So, in the air sacs you see there, you have the squamous alveolar. That's the outside of the beach ball. That's where we have gas exchange. That can be destroyed and then replenished. Then you have the greater alveolar. That's deeper. Those are the ones that are going to have the stem cells. That's the inside of the beach ball. So as they divide, they can be pushed out for the gas exchange ability. Now, far more important though, that inside layer. This is really important to understand. The inside layer of the squamous epithelium secretes something called a pulmonary surfactant. What's a surfactant? Whenever you buy any sort of detergent, you'll see a surfactant in it. Surfactants break down the surface tension of water, which kind of people like, what the hell does that mean? It makes water wetter, is what it does. What does that mean? As you know, water is adhesive and cohesive. Cohesive meaning because water is polar, it can pull itself together in an unfavorable environment to basically become a bead, as you know. It's also adhesive because it's charged, it likes other charged surfaces. Okay, fine. Imagine now you have this little tiny thin beach ball with water on the inside. Whenever you go, when you breathe out, the air pressure in the beach ball has decreased. What will happen is potentially one side of the beach ball and the other side of the beach ball could touch. Well, if you don't break down the surface tension of water with the pulmonary surfactant, water becomes sticky and I can't open the ball again, which means it ain't going to work. What the pulmonary surfactant does, it breaks down the surface tension of water in the alveoli so that whenever you decrease the pressure, the ball collapses, but they don't stick to each other because water is now less polar. It made it more fluid, so when you reinflate, it pops back open again. Okay? Failure of this is often called respiratory distress syndrome, RDS. Normally, the best way to think about it, imagine somebody has a child and it's premature. Okay? When the child is a preemie, its lungs were not ready for the air gas exchange yet because it's still in a fluid environment inside mommy. They weren't ready for that yet. Well, when the child is preemie, they lack the ability, they slow the ability to make the pulmonary surfactant. So you have to watch the baby continually. You have to touch the baby. You have to turn the baby. Why? Because otherwise, with the lack of the pulmonary surfactant, the alveoli could close and the kid could suffocate. Often they called it, God, years ago they used to call it like a crib death type of thing. It's a generic term for babies dying in a crib, but one of the main causes was respiratory distress syndrome. Again, it can happen to adults as well too. You think about what's going on right now. Any sort of agitation to the alveoli could reduce the pulmonary surfactant, meaning that they close and they can't open up and you suffocate. All right, going on down then. Let's see. We got pulmonary ventilation. Simple terms I want you to understand. When you go and you breathe in, that's called inspiration. When you go and you breathe out, that is called expiration. All right. Now, how this works. Take your hands, touch underneath your rib cage, and go breathe in. When you do that, you will feel, and there's a muscle right here called the diaphragm underneath your rib cage. Okay. So when you're relaxed and you go, you'll feel everything drop. That's because the diaphragm, when it's relaxed, bulges up under your rib cage. Whenever you actually tell it yourself to breathe in, the muscle contracts and it pushes down. That's why this drops. So one of the major things that gets air into your lungs is the diaphragm contracting, dropping. Okay, why that happens, we'll talk about in just a second. However, understand this diaphragm is holding the rib cage off of your lungs. If you drop the floor out and don't pull the ribs off, what could happen to the lungs? The ribs push down the lungs and you can't breathe. So, in between your ribs, you have your intercostal muscles. So when you breathe in, the diaphragm drops, the intercostals flex, and they open up the chest, preventing them from coming down the lungs. Now, why does air rush in? big star. This is called Boyle's law. It's a gas law. Boyle's law says this. I'm going to talk about it more later, but let me summarize it real quick. You're around a campfire with a bunch of friends, and there's drinking going on, so there's always one idiot in there that goes, oh, I have this aerosol can, let me crush it or throw it in the fire. Then everyone runs in, because they're idiots, okay, because it's a bomb. Now, why you don't compress the aerosol can, why you don't puncture it, is Boyle's law. Why you don't throw it in the fire, that's Charles's law. Charles's law basically says this, that the volume of a gas is directly proportional to the temperature with which it's at. Meaning that, as we said, if you increase the temperature, it expands. If you decrease temperature, it constricts. Volume goes down. Simple enough. That's why you don't incinerate the can. Boyle's law says this. The pressure of a given volume of gas is inversely proportional to the volume with which it occupies. Meaning this. If I take a can, which has a certain volume, and I squish it down, I've now decreased the amount of volume the gas can be in. Well, what happens to the can's pressure? It increases. They're inversely proportional. Pressure goes up as volume goes down. Make sense? You know this. You have a soda can, and then you notice when you have the soda can, you can pinch the sides in. Then you want to be a jerk to give this to somebody, take the can, shake it up. As you hand it to them, try to pinch in. You can't. Why? Because you've increased the pressure by releasing the gas in a finite volume, is what happened. Okay, and then they wear the drink. That's that whole idea. All right, now, how Boyle's law works. Follow. When you're relaxed, the diaphragm is up, the intercostal muscles are pushing down. So therefore, the volume inside your chest is lower. What happens? The pressure is higher. And therefore, you breathe out. When you breathe in, inspire, the diaphragm drops, the intercostals open up, the volume is now bigger in your chest. Therefore, according to Boyle's law, the pressure drops. Air from the outside is under high pressure to low pressure, and therefore inflates your lungs. That's how your lungs inflate. It's Boyle's law. Another way they inflate, as I mentioned, is Charles's law. Because as it comes in, your body temperature warms up the gas and it expands. But the major reason is Boyle's law. Big star, Boyle's law. All right. Other types of muscles that can be involved in breathing. Think about if you were, you just finished sprinting and you go, you're doing forced respiration. Well, think, when you go, feel, your pectoralis is pulling. Your sternocleidoids are pulling. Your muscles in your back are pulling, and therefore they're trying to open up your cavity more. Do you do this normally? No. So during what we call quiet breathing, which would be you at rest, it would be your intercostals and your diaphragm doing all the work for you. Okay? With that, we're going to conclude this first segment because I finished the gross anatomy of it. When we come back, I'm going to then go over the mechanics of it. I'll go briefly over Charles's law and the gas laws. I'll also go over quickly the other principles. And then we'll see how long that takes, if I do a third one of these or not. So we'll see how it works. All right, so I'll see you when we come back.